Well, last week we talked about the graph of e to the power x, right? We talked about the graph of e to the power x, and we have graphed it. Have you done this? No, we actually graphed it a long time ago, right? We graphed e to the power x some last week. No, excuse me, the week before last. Wait, sorry, I think I opened the wrong window. Okay, so let me open the other one for your class. Sorry about that. Okay. The wrong file did I opened should be.
Good morning, Professor. Good morning, class.
Morning. Wait. Why is this? Is this where we were? We graphed the e to the power x. That was some time ago, and last week we graphed 2 to the power x, right? And now we want to graph ln x. Okay, we want to graph natural log x. Okay, so what I do, I bring up the e to the power x we graphed, and we notice that this function is 1-to-1, right? This function is increasing function is 1-to-1. Do you hear the logic? You guys hear the logic? I want you to hear that logic, because this will be about the second or third time you heard about it, right? We did it with 2 to the power x. Okay, so let me write down the narrative. Okay, let's write down the narrative. Okay. Recap. Okay, so you need to learn how to use these narrative to build your case. And we're learning how to use these narrative to build our case, right? We have learned those important facts. What are those important facts we learned here? We have learned before. Well, we learned the definition, right? We have learned the definition of function. And then we go on to learn 1-to-1 function, right? And then what? And we learn about increasing function or decreasing function, right? From these concepts, we study the relationship between 1-to-1 function and the increasing, decreasing function. Increasing or decreasing function, they are called monotone function. Monotone functions. Okay, so this is just another word you might encounter in the future or not. So monotone means they're either just the same tone, right? You understand that word, monotone. So monotone function means a function that's either increasing or decreasing. But understand, definition of 1-to-1 function is you need to specify the domain. You need to specify the interval, typically in a domain. Okay, in domain or a specified interval. Okay, increasing function or decreasing function is on a specified interval. Or it could also be in domain, right? It could also be in domain. So when you mention these, when we mention this thing, these properties, in a lot of situations, we need to specifically mention the interval. The said function is increasing or decreasing. We also need to mention the interval where the function is, having the specific characteristics. That's important. But when we talk about this particular function, e to the power x, sometimes you don't need to mention, because if you don't mention, by default, the listener or the reader will assume it is on the interval of a domain. It's on the entire domain. And that's in the case of f of x equals to e to the power x. Right? So we did this before, right? We did this before. So now we are about to study ln x. It's inverse, right? So in our narrative, we know these facts, right? We knew these facts. We knew these facts. So we can use these facts. We can use these facts. Do you guys follow me? So I'm going to show you how you use these facts. And you definitively need these skills in calculus. Okay, one, A leads to B, B leads to C, C leads to D. Okay, so one build on top of the other. You keep on building, you keep on building. Okay, so what are these facts, right? We mentioned these facts before, is that a monotone function is a one-to-one function on the specified domain. Okay, so I'm going to write it down. And increasing function is a one-to-one function. An increasing function is a one-to-one function. How do we know that? You just compare the definition. Just compare the definition. So you start with an increasing function, and then you know you can prove it's a one-to-one function. We have proved that. We have proved that. So this is a fact. So now this fact can be used by you, by me, by anyone. By anyone. Okay, and of course, you can also say a decreasing function is a one-to-one function. Look at these words. Look at these words. We use the word an or a. What does that mean? It means anyone. Anyone. Any increasing function is a one-to-one function. Any decreasing function is a one-to-one function. Okay, if you want to be more rigorous, okay, on domain or a specified interval. On a specified interval. Okay, so you always refer to a specific interval. If you don't refer to the specific interval, by default, people will take the domain for that function and use it. And then we're going to examine if your statement is true or false, right? Because once you apply these rules to the specific function, we have to know the specific function's domain and range or your specified interval. So it's an absolutely rigorous process and a rigorous narrative. The narrative itself has to be rigorous. For example, if I made a mistake, which I did, right? No matter where I go, it's a mistake. I can choose to admit it early, or I can choose to fight it, and eventually I will have to admit. So my policy is once I made a mistake, I will correct it as soon as possible, apologize, whatever I have to do. Mathematics is just like that. If it's true, it's true. If false, it's false. Whether you admit it or not, it's very, very objective, I would say. Okay. Anyway, so without further ado, so let's look at these wordings. I spend all this time on with you guys on these wordings. I hope you guys pay attention to it. When you listen to these lectures again, you better pay attention. These are the narratives, and the way we make the narratives is going to be the key to your success in calculus class. Because in calculus class, you need to build your case from limit to continuity to differentiability and to other future theorems. One is built on top of the other. Okay, so your mind needs to be full of definition, full of theorems, and with the understanding of them in order to be successful. In order to be successful in those classes. You guys follow me? So I'm training you to do that with these, concepts you have learned up to pre-calculus. And the next fact we're going to talk about, which you're also familiar with, because we mentioned this when we were building the 2 to the power x and the log base 2x, right? Is that a 1-to-1 function has a unique inverse. Okay, so supposedly we have a 1-to-1 function f. So sometimes we introduce a symbol in our narrative in order for future connection, for future usage. Okay, so a 1-to-1 function has a unique inverse, which we call it f inverse. This will also be on domain or a specified interval, unspecified interval. So you always, when you say something, you have to tell the reader where this happens and what it is. Okay, where it happens and what it is. Anyway, so we use these 3 facts. Okay, I'm going to build a little case for you. This is, very simplistic case if you compare all those things you have to do in calculus, right? All right, so now I have a function f of x e to the power x. Then you can say this function, right, is an increasing function on its domain. Thus, it is a 1-to-1 function. As a result, it has a unique inverse. And let's call that inverse f inverse. And what is that f inverse? What is that f inverse? We know how to find inverse, don't we?
Would it be y equals ln of x?
That's right. That's exactly where we're leading, we're leading ourselves to. Okay, then you understand how to find inverse, right? You see, a lot of things you guys have learned in the past, okay, whether you remember or not, I'm bringing them together as a whole. And now, of course, you're going to go about to find the inverse, right? To find the inverse. And then, so you have this narrative as you prelude. And then you say, okay, let's find the inverse. And we know how to find the inverse. Okay, you put this y here, and then there's step 1, step 2. The first step we do, this is the second time we do it. No, actually third time we do it, but with exponential logarithm, this is the second time we do it. Why do we repeat it? Because they're important. Okay, they're important. And this is something I wish you to learn. So when we do step 1, step 2, we swap the x, y. And step 2, what happened when we swap? When we swap x, y, what happened also along with the swap of variable? I mentioned before. The swap of these two intervals also leads to the swap of a domain and range. Okay. Now, with that, well, we're going to find the inverse, right? So solve for y. Right? The same procedure you have learned a long time ago, right? So from this guy, right, from here, hold on, sorry. From, right, f of x equals, this is x, right? Solving this, right, lead us to what? Right. Solving this lead us to what? The definition of logarithm. The definition of logarithm, right? That's how we got what? We got y equals to ln x. Okay, so is everybody with me? Right? Recall the definition of logarithm. And what is it? Log base b of omega or baloney is equals to what? Triangle, whatever symbol you use, is equal to b raised to the power of what? The triangle equals to the baloney, provided, okay, there's a little accessory about the base. What is that provided? What is it? Does everybody know? Everybody must know. Okay. If I ever forget to type this, you should remind me. Okay. So how does this guy, right, in the exponential form related to this guy? Right? You go through that process. You go through that process. Base E is indeed larger than 0, not equals to 1. So here you just switch places. So this is x, right? B to the power triangle, b to the e to the power y equals to x. So your omega is going to be in this place because omega is x, right? You just match places, right? So you can put this behind if that helps you to make the match, right? So the symbols, the name of the symbol doesn't really matter. It's the position matters, right? It's like you play a chess game, right? It's the position matters. You guys see that? But these two functions are inverse function to each other. Okay, so you can see that connection. So next, we're going to call this function f inverse equals ln x. At the same time, domain and range is already set for it, right? What is the domain for f of x equal to e to the power x? What's the domain for that? Can you guys tell me? What's the domain for this? There's that one sentence statement. Absolutely useful. Absolutely useful. So what is that one sentence statement for domain and range for function equals to e to the power x? Can you guys tell me that? What is it? Everybody, have you guys awakened up? Are you awake?
The domain will be negative infinity to positive infinity.
Domain is all real numbers. Absolutely good. Yes. Negative infinity to positive infinity. The range,
The range would be 0, comma, positive infinity.
okay. Can you use that, my favorite form? X larger than 0, X less than 0. No, wait, Wilbur, you said 0 greater than X. What does that mean? That means X less than 0. What does that mean? What is that for? Wilbur, what is that for? X larger than 0 for the range is completely wrong. X is the input. The symbol X is for input. X belongs here. You messed up domain, you messed up input output. You either say f of x under the circumstances or e to the power x. If you say x is larger than 0, you get 0, sorry. Because in this context, x refers to the input. The input from should be all real numbers. Okay, you don't just pick up any symbol. Yes, the symbol doesn't matter. But once you have a context, once you have a setting, you have to be consistent with your narrative. If in your narrative, X represent input, then, and you use it for the expression of output, then you'll be completely wrong, right? Your reader will be very confused. That's what I'm saying. Your reader will be very confused because if you say here, f of x, you already set up your context, okay? You have your f of x e to the this is the rule of the function, and you use x as input, and then you tell the reader the range is x is larger than 0. Your reader will be completely confused, and your professor who grades your work will be completely confused, and she has no choice but give you 0. Because if she doesn't, she would make herself a laughingstock in front of her colleagues and all the mathematicians in the world. Do you understand? Because math is either right or wrong. All right. So the range has to be expressed this way, or some people like to use this one. That's how we see the confusion. A lot of you guys know these two. But when it comes to express using the symbols or using when you need a useful symbol, such as this, I don't know why our students are so confused, right? That's why I insist you have to, in your description of domain and range, you have to tell me or tell yourself, you understand this is the input and this is the output. You have to express the input output properly, correctly to get your credit. Do you understand? Okay, I hope you understand. You can't just pick up any symbol. Oh, this is greater than 0. No, In your expression, you are already telling the reader what is the output. And that output is positive, okay? So this narrative is very, very important, okay? So wrong, so let me put it there, wrong, or wrong. Right, sometime I want you guys to have a good laugh because that confusing last name probably confused a lot of people. So it's just wrong, okay? But anyway, this narrative is saying e to the power x is larger than 0 for any real number x. This is the domain range in one sentence. Very, very useful. Well, can we have another way to say it? Of course, you can say e to the power x is always positive. Can we see that? No matter what x is. We write this down, we use these words is to enhance understanding. Okay? Is to enhance understanding. All right, so that was quite a long review. So now we talk about the domain and range for ln x at this moment. At this moment, when we swap the xy, at this moment, the domain and range for ln x, it's already decided. What is it? One's domain and the other's range, right? The domain for e to the power x is from negative infinity to positive infinity. The range is positive numbers. So the domain at this moment is already decided. The domain now, the input would be what? Larger than 0. And the range is what? All real numbers. All real numbers. i.e., that is ln x, okay? ln x can be any real number for x larger than 0. Okay, so at that very moment when we swap, domain and range is already set. Now the question is that correct? Does that make sense? Is it always so? Yes. We talk about for any pair of inverse function on specified domain, on domain or specified interval, this relationship is forever true. You swap, domain and range swap, so the domain range are set for the inverse. Now we're going to graph this and we're going to reinforce it. Okay, a common mistake. A common mistake. Okay, people will say the domain for ln x there are all kinds of mistakes, okay? Positive. And this student will say the range is also positive. Okay, people will give these answers. Domain is from 0 to infinity. The range is also from 0 to infinity. That's another mistake. And of course, we have all kinds of mistakes. We have all kinds of mistakes, right? On this answer, of course, you understand this piece is right, but this piece is what? This piece is wrong. Okay, for that reason, to correct this mistake, okay, this mistake seems to be perpetual. I hope it's not eternal, right? We're going to plot points. We're going to plot points. So now everybody, please roll up your sleeves. We want to confirm, okay, in the process of plotting points, we want to confirm that the domain and range for ln x indeed should be this. You guys follow me? Okay, so let's do it. But we graph ln x as the inverse, okay, as the inverse function. So now let's graph it. Graph this function. To graph this function, I want to use a little bit of use something we have done before, and I want you to witness what is the process. This little process is just make you to have that connection, right? And so I want you guys to get the tables that we did for ln 2 for log base 2x, log base 2x. So let's find that table. Okay, we graphed the log base 2x, didn't we? You guys see this? You should have a table like this in your notebook. Okay, so please find that notebook. Find that page of notebook. While you're graphing ln x, let's see what has changed. Let's see what has changed. In my observation, most of the students who have heard of ln x, they never graphed it. Because it would be very typical, the professor would tell you, oh, we have graphed log base 2x, and maybe, and ln x is similar, and this is how it looks like, and they never go into details. For good reason. I'm not saying they did anything wrong, for good reason. The students in turn that they should do it themselves. Who will do it? I think none of the students would do it if the professor doesn't do it. Is that right? Okay, so let's do it together. Let's do it together. Okay. I want you have this table next to you. Can you guys just take a picture? Because I'm going to make changes over it. I'm going to make changes over it. So you see, what is similar? What is that details? The devil details, because we often say the devil is in the details, right? What is that details that makes the difference? And what is the difference? And where is the difference? And what are the sameness? Okay, so if you like, and go ahead and take a picture of this table. Okay, you should have this table in front of you. All right, have you taken a picture of it? Yes? I consider that done, okay? So now we did log base 2x. We did each one of these last week. So now we're gonna work with ln x. What's the difference? The difference is the base. Nothing else is different. Domain is the same. Now we want to confirm why the domain has to be like this, right? So everything is changed to base 2. So all of these log base 2 is going to be ln. It's going to be common. It's going to be natural log. Everything here is going to be ln. You guys follow me? Everything will be ln. I want to make these changes in front of your eyes because I want you guys to see that's the connection. That's what your professor said before, that similarity. Because this is a different base, the former input would not be producing the same output. Okay, for example, ln 2 to the power of -100 is not going to make it to -100. So all of these will be wrong. Are you guys with me? So if I only change the ln, right? This will be wrong, this will be wrong, this will be wrong, wrong. Do you guys follow me? Because if you all you have to do is just plug in your calculator. You know it's not going to give you the same answer, right? Could you plug in these numbers in your calculator? Say 1 over ln 1 over 32. What would that be equal to? I assure you, it's not going to be -5. Are you guys there? Well, provided that you have ln on your calculator. Some of your calculator problem may not have ln, right? So then what you do? I assure you there. So all of these are going to have to be changed. All of these are wrong. So we have to make a lot of changes. You see, just one change of base, make some changes. So these are the differences, right? The actual numbers, the input and output may need to be adjusted. So let's see how we adjust it. Okay. All right. On the 0 part, we're going to come back to it. Okay. On the -2 part, it's okay. I can change it to -e if I want. Okay. I can change the input from to -e. Okay. On this part, I'm going to change it to e to the power of -1,000,000. Could I do that? Of course I can, right? And this will make it right. Do you see that? So if I change the input from e to the power of -1,000,000, the output will be -1,000,000 by definition, right? If I change this to e to the power of 100, all of these output are still all of these input are still positive, right? And this will be e to the power of -100. So the output will still be -100. And this one I'm going to change to e to the power of -10. Then you say, why do you change it? Because I want convenience. The former number can still be input, but they're just too messy. I want to choose numbers to make my life easier. That's why. Okay, I can still use those other numbers as my input, all right? I just don't want to deal with the mess. Okay, so now, so if I change this to e, I will still get the same output. Do you guys see that? And on this one, how do I change it so that I won't have to deal with the messiness? Well, I can use e to the power 5. I think soon enough, you're going to get the hang of it, don't you? Have you got the hang of it already? So this input, instead of being 1 over 2 to the power 5, I'm going to use 1 over e to the power 5. Okay, so 1 over e to the power 5. And that for sure is going to give me -5. Do you guys follow me? And of course, my input need to be changed here on this side, right? So this is e, this is e, and this is going to be e to the power -5. Right? Does everybody follow me? Slow me down or tell me to speed up, okay? 1 over 16, for my convenience, I'm going to change it to e to the power 4 under 1, which is e to the power -4. Why do I do that? Because it makes my life easier. Okay, so I'm going to plug in this one as my new input for the new base. And then I will make that -4 as output. So this new input will be such. Have you got the hang of it? This is a little trick, okay? Once you know how to do it, it's no longer a trick. It's not a trick. You realize it's probably obvious to do it this way, right? And next, what would you do? I want you to make the changes for the following numbers. Have you guys got the hang of it? Can someone say something? Does that make sense?
Yeah.
Are you doing it? Are you doing it? I'm doing this really is for you. I have to tell you, in the entire classroom, the only person who doesn't need to do this is me. Every one of you need to do this. This is the activity you're building your foundation. Okay, then we're gonna start to observe the table. Once you've done this once, maybe a couple of times, oh my God, you're gonna be so good. You will have an intuition, you will have insight. You just need to do something as simple as this. And you will have a little bit easier time in calculus, I assure you. Because this function ln is going to be used in Calc 1, Calc 2, Calc 3, and beyond. Okay, so now this is going to be what? E to the power 2, -2, e to the power -2. So we get to the -2. So here e to the power -2. And over here, it should be e to the power -3, right? And keep going. So this is 1 over e, 1 over e, 1 over e, output. So 1 over e. It's really a minor change, isn't it? One stays because ln 1 is still equal to 0. And this guy, I'm going to change it to e, and this guy, I'm going to change it to e to the power 2. E squared. E. 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 E squared. Once you've done it, what do you say about what you have done? What do you say about what you just have done? Can any one of you comment about what we just have done and what you have done? What would you say? No one said anything. Are you guys ignoring me?
I'm just doing the work.
Okay, keep going. Okay, once you're done, okay, I want to hear some comments on the chat. I want to see people say, oh, this is so hard. Or someone say, oh, this is so easy. It's obvious. Or whatever comments you like to make. Okay, feel free to make it. Does anyone need any special help from Farouz?
I'm here with my calculator.
I know, there he is. He has a calculator with him. Are you done? No, I'm not rushing you. I want to take your time to do it. especially for such an important function, right? Then what? Maybe I start to see some comments. Feel free to comment, speak your mind. Of course, we're not done yet, right? We have to go back to the top about 0 and negative number, right? Because in this process, we want to figure out the domain and range as well, right? So this little table has a lot of treasures hiding behind the surface, because you look horizontally, you look vertically, and you have a little you use a little imagination, right?
Professor, your main question was the difference between domain and range between the function and its inverse.
Right. So now we're doing ln x, which is doing this function, which is the inverse of e to the power x. And of course, after that, we're going to bring them together, right? But we do gradually. I want you guys to do it with me. Okay. So now, has everybody finished?
Mhm.
All right. So what do you see? Is this something easy for you? Is this something difficult for you? Nobody made any comment. I was hoping to see someone say, oh, this is so hard. Or someone would say, this is so easy. Or someone say, oh, this is obvious. Something like that. No comments.
I remember, Professor, when you were accompanying this table with its graph, that would be visual representation.
Yeah,
which
we're
was
going to
very
graph
helpful.
next. We're going to graph next.
Okay.
Of course,
Thanks.
well, of course, we're heading there. But just
Thanks.
for the calculation, does anyone have any questions about these, how we get these numbers?
No.
You guys all got those numbers, right?
Yeah.
Okay, good. All right. And this is only observing from the perspective of definition. Okay, we haven't done the graph. Of course, we're going to do the graph. Okay. So now, for 0, because this will be something we consider for domain. So far, all the input we have chosen, right? This input, very small, positive. All of these inputs we have chosen here are positive. We have chosen 1, 0. We have chosen 1 negative number. For input 0, what will be the output?
I want to say it's not possible.
It's not possible. That's right. It's undefined. Just like for log base 2 of 0, there's no answer. So for this input, there's no answer, right? There's no output. And the definition of function says for each input, you have to have a unique output for that input to be qualified to be in the domain. Do you guys hear that? I've said this many times, right? Why? Because they're so important, and that's the guiding principle. How many guiding principles do we have? We have 6 principles, just a handful of definitions. That's all. But those those principles and definitions are to be used. If you use them, the more you use, the easier you get. The more you use, the simpler it gets. All right, so for this one, okay, but I want you to quote, I want you to cite that very powerful statement. Okay. What is the output for that? Because whatever output it is, right? Suppose it's a triangle, that e to the power triangle has to be what? Has to be equal to 0. And this is not possible, right? This is not possible because of what? We just spent so much time to review, right? E to the power x is always positive for any real number x. Therefore, there's no output. You guys follow me? This is a powerful statement that's waiting for us there. If you go back to the definition, we talk about definition to the king, right? Or pharaoh, or emperor, or whatever you call it. Definition to the king. All right, so this is also undefined. So 0 cannot be in the domain, right? Can negative number be in the domain? Can negative number be in the domain? Right? Could it be in the domain? And this has to be negative e. And for the same reason, there's no output. Do you guys see that? Remember the mistake I mentioned earlier? Okay. I just don't want you guys to make those mistakes ever. All right. So this is undefined. So in the domain, the input cannot be 0, cannot be negative, can be positive. So what would the domain be? Input has to be positive, right? Input has to be positive. Do you guys see that? Are you convinced? Because I don't want you guys just to memorize. I want you to understand, okay? The fundamental reason is that from that definitional function, for these inputs, there's no output. Therefore, these inputs are not qualified to be in the domain. Therefore, no points. So now let's graph. Let's graph. Okay, let's graph. Before we graph, okay, did you notice I have arranged the input in what order? In what order? In this direction. Is it from larger to small or small to larger? Huh?
I want to say small to large.
Of course, that's right. But let's look at the output. What do you see in the output? Right now we know that the domain can only have positive numbers, but let's look at the output. Some of our output is negative, some of our output is 0, some of our output is positive. So what do you say about range? The range has to be from negative infinity to positive infinity, right? Do you guys see that? Yeah? Okay, let's graph. Graph. So we got so many points, right? And we want to graph, want to get some, we're gonna get a couple of we're gonna get some points. We're gonna get some points, okay? And I'm just gonna set up, have you set up your graph? I gotta choose this one. This is 5, 10. All right, so I got this graph, got the grids. Okay, we're gonna plot some points together. Do you guys have a paper pencil in front of you? Please do. So we have all these input output to plot there. So let's start with something simple. Which one is the simplest point in your eyes? Which one? I'm sorry? Someone said something I didn't quite hear.
1,
1, 0, right? Yes, to me too. You see, great minds think alike. 1, 0. We start with something simple. Okay. So I'm going to put that point on my graph. And then I realize that point is very special, isn't it? Is that point very, very special? What would you call it? What would you call it?
Our x-intercept.
X-intercept, that's right, because that's where the curve crosses x-axis, right? And what is the next simplest point for you?
Probably e to the 1.
E comma 1, right? Well, we can decide which one. So now I want you guys to plot a couple points with me, okay? So I'm just going to keep going. So this point, E comma 1, right? E comma 1. You just, when you do it on paper, you just estimate the E. E is about 2.7. Just put 2 point, about 2.7. Nobody is going to check you for accuracy. So in order to compensate that, you want to mark the point. Okay, we're going to mark the points a little later because the limitation I have here. Okay, so I'm going to plot one more point here on the above. Is everybody doing that already? Okay. And then I'm going to plot some other points that give me negative output. You see, I plot some points that give me 0 output, and I plot some points that give me positive output. And I didn't plot all of them. That's okay. I'm also going to plot some points which give me negative output. Okay, negative output. Right there. Okay, and one more. Feel free to plot more points if you want. Okay, and you can imagine that these points, you can see from this direction, right? As x is getting closer, and closer to 0, right? What do I mean by that? The input of 1 over e and the input of 1 over e squared, 1 over e squared is closer to 0 than 1 over e, right? And the output is getting lower and lower. Do you guys see that? because that's what these 2 points is about. Okay, so let me mark those points. So when you do this, you are being mindful. 1 over E. Okay, forgive me. So this is 1 over E. This point. And that point, 1 over E squared. Right? You follow me? So 1 over E squared is closer to 0, which is over here. 1 over E is over here. So 1 over E squared is closer to 0 than 1 over E. Do you guys hear my words?
Yes.
So as our input is getting closer and closer to 0, what happened to the output? The output is getting lower and lower, right? Right?
Yeah.
So if we keep plotting these points, what will happen? The dots is going to drop lower and lower and lower yet, right? Is that right?
Yeah.
But the input will never touch 0, always larger than 0. But it can get infinitely close to 0. So the red dots will just keep dropping and dropping and lower and lower and lower and lower. Yet even, get to negative 1,000,000 and even lower, because I can choose another input closer to 0, such as e to the power negative 1,000,000,000. And that output will be negative 1,000,000,000, so even lower than negative 1,000,000. Are you guys following me? And unfortunately, that can only be done in our imagination because the software cannot do justice to it. Okay, this is the imagination I want you to put on. Put on your thinking cap. Okay, so are we ready to connect the dots? So let's connect the dots. So in this direction, as x getting closer and closer to 0, what happened to the output? The output is getting what? Lower and lower and lower yet. So that's where you get the negative infinity, because you can get as low as possible. And on this graph, this piece of graph is negative. Output a negative. This piece of graph is positive. And there's a point that's 0. Output is 0. So output a positive, 0, negative. So the output for ln x can be negative, positive, 0. All real numbers output. Is that clear, everybody?
Mhm.
Is that clear? Is that crystal clear to you? It has to be. That's my goal.
With the graph, yes, Professor.
Okay. So now let's mark the points. Since we're here, let's do it. Let's mark the points. When we're marking the points, I want you to reflect on what I just said. Okay, and each one of you is going to mark your points, right? This is 1, 0, right? Input 1, output 0. Input E, output 1. This is an increasing function, isn't it? Because as input gets larger and larger, the output is getting larger and larger, right? Increasing function. The input is e to the power negative 1. The output is negative 1. The input is negative 2. The output is negative 2. right? It's an increasing function. What else? In this direction, if input gets larger and larger, what happened to the output? The output is getting what? Higher and higher yet, right? So that you can see the domain is all positive number, the range is all real number. I understand that some of you may be puzzled, right? Maybe puzzled by this. Well, your input are all positive number and your output are all real number. Isn't that real number set larger than all positive number set? Right? Could that be something you're thinking? Yeah? Well, this same question was thought about by mathematicians hundreds of years ago. They thought about the same thing. That's why they say, oh, this is a one-to-one function. There's a one input, there's exactly one output, and vice versa. Right? Is this set of real number really larger than the set of positive number? They're all infinite. They're all infinite. The question is, how do you compare infinite? The question is how you compare infinite. In fact, you can match them one-on-one for sure. So sometime because I've been thinking about why our students make those mistakes, right? Some students will say the domain is greater than 0, therefore the range is going to be all greater than 0, which is completely wrong. I don't know what's on your mind, okay? So please let me know if you have such questions, because it's totally, understandable, okay? I would admit that when I was a student, I probably have thought about these questions too. I didn't keep a diary, but I might have, yeah. But these questions were thought about by lots of people. So you are not alone. So if you talk about the real number set and the all positive number set, you really cannot say real number set is larger than the positive number set, because both are infinite. How do you compare one infinite with the other infinite? Right? All right. Now, it's time to summarize, isn't it? Yes?
Yes. Yes.
All right.
I had one little comment regarding that infinity, Professor.
Please go ahead.
The comparison between those infinities, one greater than 0, the other all real number. All real number infinity covers the directional infinities, positive infinity, negative infinity. And if you apply it to human being, we living all on planet Earth, that's what is the limit of mankind. Toward positive infinity, selflessness. Toward negative infinity, evilness, selfish.
I never thought of that.
So thanks.
Some people comment where we human are between angel and devil, and well, fortunately, that's not a subject I have to teach. Okay.
So in past 40 years of my academic hobbies or life or mind thoughts, I noticed that math science can help me solve many problems as a human being. So it's just amazing how we can use the math science, even all these concepts. And I noticed you use the E when we have a ln. How significant is use the E is easier than use any other number when we are dealing with ln.
Yep, absolutely. Okay, if you don't have any question, we're going to move forward, okay? We're going to move forward and we're going to do the summary as we did before. So now, okay, I'm going to clean up a little bit. So let's summarize. So this curve, right? We're going to bring this curve and e to the power x together, right? E to the power x in the same picture. Okay, we're going to bring this curve with e to the power x in the same picture. And I'm going to give e to the power x a different color, right? And I'm also going to make some adjustment. So the first one of comparison is going to be between ln x and e to the power x. Okay, that's the first comparison. Okay, the function of f of x equals to e to the power x. And the next one is this guy. We know that these are two different rules, but these two rules are related. Okay, these two rules are related. So input x. Okay, this rule is f of x. And that's the rule. And the output is e to the power x. And the other rule okay, f of inverse x equals ln x. So the output is ln x. Okay, so we're gonna, and we have their separate graphs. We have their separate graphs, right? And they're graphed together. Because they're separate graphs. Right? And they're graphed together. Domain range. What's the domain to e to the power x? I'm going to plot a couple points for you. Okay. Okay. Domain range intercepts. Are you guys there?
Yes.
Domain, what's the domain for e to the power x? All real numbers, right? Range. For any real number x. right? And what's the domain for ln x? So today we have done this many, many times already, right? Input has to be positive and output is what? All real numbers. You can see from different perspectives, from the perspective of inverse function, from the point we plotted, from the graph, right? I just want to ensure none of you will ever make those mistakes that was so rampant. Now, what is the x-intercept for e to the power x? Are you there? Are you guys there?
Yes, I'm just writing this down.
Is it 1, 0 for e to the power x? Is this what you meant, Maritza? Is that what you meant? Okay. Does everybody agree with it? Choice A, choice B. What is x-intercept for e to the power x, guys? Thank you for your contribution. That's right. It's none. You see the curve never touch x-axis. How, where do you get the x-intercept? None. Okay, self-correction is always the best. What is the y-intercept? That's right. How about ln x? What's the x-intercept? What's the y-intercept? ln x.
The x-intercept would be 1, 0, and there would be no y.
That's right. Great, great job. Okay, none. Okay. Now, I want to give you guys some perks that you need in calculus class. Okay. And when we put these graphs together, what do we see? One is a reflection of the other, right? Over something, right? What is that something, the two curves reflecting over? What is that something, the two curves reflecting over? What is it? What is this line? What is this line? It's y equals to x. Okay. All right. So next, I'm going to give you some other perks. These are real perks that you definitively can use in your calculus class. Okay, but we have observed, right? Since we have observed those phenomena, so I'm going to give you like little perks, a little introduction to your calculus classes. Right? Now, when x approaching negative, we're talking about e to the power x, okay, this first curve. When the input approaches negative infinity, what happened to the output? The output, the green dots is getting lower and lower. We talked about this before, right? E to the power x will be approaching 0 from larger than 0. okay? Because the curve is always above x-axis. It never falls on x-axis and never falls below. Therefore, e to the power x is approaching 0, and we put a little positive sign on the shoulder of 0, meaning that it's always above 0. Okay, more than 0. Okay, a little, even if it's just a little bit more than 0, it's above 0. Okay, now, so this is the description when the input approaching negative infinity, the output is approaching 0 infinitely. Okay, so now the next line, as input approaches positive infinity, what happened to e to the power x? And of course, it's approaching positive infinity, because if we go in the other direction, right, as x getting larger and larger, the output is getting higher and higher yet. So these obvious traits we have observed now is written in the language of calculus. And you're going to learn other symbols, so I'm not going to introduce the other symbols for you, but this is just a plain shorthand notation. It describes something we have already observed. Okay, so now look at ln x. Look at ln x. ln x, you don't have x approaching negative infinity because x cannot be 0, cannot be any negative number, right? But x can approach what? It can approach 0, right? X can approach 0, right? So x can approach 0. We just talked about this. As x approaching 0, as close as possible to 0, okay, as x approaching 0, as close as possible to 0, what happened to the output? The output is getting lower and lower and lower yet. We just observed that, right? So what do we say about that? Well, this is what you say in calculus class. As x approaches 0 from a positive side, you see, we're complying with the domain. Because if you don't have this positive sign on the shoulder, you might lose a point or two. I'm sorry, because it could be from the negative side. All right? ln x approaches what? Approaches negative infinity. That's how we describe this corner. Okay? And of course, as x approaching positive infinity, what happens? What happened to ln x? As x approaching positive infinity, okay, as x approaching positive infinity, getting larger and larger, the input getting larger and larger, what happened to the output? The output is getting higher and higher yet. Yes, it's going to get even higher, as high as you want. Don't worry about that. This piece is going to keep going up and up. It looks like a little slowly, but surely. Okay, so therefore, as x approaching positive infinity, ln x is approaching positive infinity. Right? Now, we have these two pictures together. We have these two pictures together. Right? Let me clean up this mess. If you look at this picture, okay, I'm going to bring this picture to the top. Right? Have we done something similar with 2 to the power x and log base 2x? Have we?
Yes.
Can we get that picture, put them side by side? Let's do it, right? This process is called a study, okay? I'm gonna find that picture, and you do too. I think I found it. Yes, I found it, right? If we put them side by side, can you tell which one is which? How do you tell which is which? They look alike, don't they? So if I change them to be the same scale, can you tell them apart? It's a little bit hard to tell them apart, right? You have to dive into the details. Of course you can tell them apart just by looking at the points, right? Do the measure, do the, you know, but how about we put them together? How about we put them in the same graph? How about we put them in the same graph? Which one is, you know, wider, which one is more narrower, and so on and so forth, right? So that will be clearer, isn't it? Are you guys with me?
Yes.
Shall we do that?
Very good idea, person.
Thank you. Okay. So now I'm going to, so this is my, so let's mark the curve, right? Mark the curve because I don't want to get confused. Ln x, right? We did this. And this guy is what? E to the power x, right? And this is what? This is ln, this is a log base 2x, right? It's very hard to compare them when they're not in the same picture, right? So now we want to bring them to the same picture. All right, so let's do it. I'm going to graph 2 to the power x in that picture. Let's choose a color. Maybe blue. 2 to the power x. You see on this side, on the other side, do you see that? How about log base 2x? Log base 2x. Let's choose a color. Purple. So this black one is ln x. So now let's mark some more. Okay, so this is 2 to the power x. And this one is log base 2x. My marking is not ideal because I would make it a color coordinated. But at least now I mark it, okay? I know I'm gonna have to mark it again. Now, this is the time you're gonna imagine, right? You can see domain, range, intercepts, and those perks, they're all similar, aren't they? Okay, and you guys should work on summarizing it because I can't do everything in class. Okay, I already give you the, you know, the foundation, right? It's up to you. But next, my next question is, what if I graph 3 to the power x and log base 3x? Where do you think they should be in this picture? You know what I'm talking about?
Can I answer or wait?
Please wait, Farouz. If I graph 3 to the power x in the same picture, log base 3x, okay? We know the shape is going to be similar, but they have a relative, it should get narrower. Okay, so let's see. Okay, so let's graph log base 3 to the power x. 3 to the power x, I'm going to use red. Are you ready? Yay, you got it right. Okay, so this is 3 to the power x. How about log base 3x? I'm going to use red again. Are you guys ready? Have you made your guesses? Is it going to be higher, lower, or in between, right? Is it going to be higher, lower, in between? What do you think? This will be
Higher?
on this clutter, right? This is one family, this is another family, right? Ha. That red one is log base 3x. Okay, one more thing. How about 10 to the power x? How about 10 to the power x? I think my screen is freezing. It's frozen, sorry. Okay, so how about 10 to the power x and the common log x? How will they be positioned? It will get narrower. Oh, wait, that was the answer earlier. I'm sorry, my screen is frozen. Okay, let's see, what can I do? Okay, keep your imagination, okay? We're getting closer to the end of the class, so. But your quiz will be about this. Okay, we will not be doing 3 to the power x log base 3x in class, and we will not be doing 10 to the power x and common log x, but you should be able to answer that quiz question as they're going to be related to all 4 curves. Okay, I have been contemplating these questions for you, you know. The relative position, okay, shows us that number one, we have 2 families here. We have 2 families here, right? One is exponential function family. One is a logarithm family. After we have studied them thoroughly, then you know that in your calculus class, you're just going to be using e to the power x and natural log x. That's all you use most of the time. You rarely use the other functions. But it's very important to understand these functions because you might need to use these functions in your own specific fields, such as biology, social science, and things like that, right? But you can see all these. The reason why they're called in one family because they have so much in common. And of course, humanity at large, we have a lot in common. But at individual level, you can see these are being classified as different families. Okay, so I cannot find my cursor. Okay. Anyway, I will give you guys homework. Okay. And I think you get it. And I will see you guys tomorrow.
Thank you, Professor.
Thank you, guys. Thank you.
Thank you.
Thank you. See you tomorrow.
I'll see you guys tomorrow. Great job. Okay, make sure you do these groundwork after class. Maybe just one more time, right? One more time, right? All right. I'm going to try to close it. I'll see you guys tomorrow. Bring your questions with you. Have a great day. Where is my cursor? Let's see. control. Task manager. All right. I think I have to do the ultimate thing. Oh, okay, that actually did get deleted. Oh, okay. Hold on. Come on.